Good morning, everybody. How was your weekend?
Too short.
You forgot about the exam, right? What exam? You got started on chapter 12, so I don't have anything to teach you today. It's all set, ready to go. No.
Yes.
I really only have two things to teach you today. I'm going to give them to you right now, and then I'm going to go home. That's it.
Okay, thank you.
That's chapter 12. Okay?
All right.
You think you any better than that?
Okay.
Yeah, good luck. So, good luck. Why the screen died. Come back. That would help.
I'm tired.
All right. So, what kind of things in our world, the universe, our daily lives, whatever, what kind of things would we want to have these two conditions on? So, we're trying to say here that we don't want any net force. So, if there's no net force, what do we know about the acceleration? It's got to be zero. So, its motion isn't changing in a linear sense. What's the second one say? No angular acceleration. So there's no kind of rotational, any kind of change in motion. So what kind of things do we not want to accelerate in any way, shape, or form? What? Buildings? Do you want the net force to be zero on this building at all times? Yes. Why? Because if it isn't, then this building's accelerating, and we really don't want that. Do we want the net torque on a bridge to be zero? Why? We don't want any bridges rotating. Right? So, what we're talking about in chapter 12 is something called equilibrium. In engineering speak, they call it statics. So, yeah, class over. This is Manhattan, right, New York City, and everything in that picture, besides the cars, hopefully, is in a state of static equilibrium. We don't want any acceleration anywhere. Now, that seems kind of boring, though, right? I mean, like, okay, so everything's equal to zero, we can go home, right? No. How many of you have to take statics for your engineering majors? Okay, you are going to spend an entire semester doing this. What I'm going to do in one day, you're going to take an entire semester to do. What does that tell you? It's important.
It's really important.
It's not as easy as it sounds. And there's lots of different methods for going at this. Engineers have come up with some really brilliant ways to figure out what forces are doing. As an engineer, you want to know the forces that are in the supports and the struts and the connections and everything that's going on there so that you know what materials to use and how strong they need to be to support a given foundation and all these different sorts of things. So we're going to dive into all that and start talking about that static equilibrium. So the name of the game is that we've got to make sure that every force and every torque add up to zero so that there is no acceleration going on whatsoever. So as a demonstration of this, let's talk about helping people move. Now, before I get there, realize that in physics, we play a little bit looser with what we mean by equilibrium, because we can have those two conditions be true, and the object can still be moving. So a really good example of this would be your car with cruise control on. Okay, the sum of forces is zero, sum of torques is zero, but there's still motion. In engineering circles, when they say statics or they say equilibrium, they mean both. There's no change in motion and there's no motion. So I'm going to be careful. I'm going to make sure that we stick to the engineering definitions for chapter 12, right? So in both of these cases, not only is the acceleration 0, but the actual movement of the object is going to be 0 as well. So let's talk about carrying pieces of furniture or boxes or things like that. Let's say that there's you've got a table or a board or something between you and your friend, okay? And you're both holding on to the ends of this board. So there's going to be forces involved here, right? There's going to be a force from the person, right, on either end. The object itself could have weight. I'm going to leave the weight out of this example just to keep things simple. But if this were a uniform board, where would we draw the weight vector coming from? In the middle, at center of mass, right? And if this was all you were doing, you were just helping somebody carry a table or a board, then what would you say about the forces between you and your friend? They'd be equal, right? Because you're both, right? Same weight, split between two people. Okay, fine, done. But let's say that you're a friend with me and put the box of dishes closer to your end of the table, right? So here, okay, we have a situation where we know who is going to be carrying more force, right? Who is it? F2, isn't it? Because that box is closer. Let's see if we can use our statics, or our static cases here, in order to figure this out. When we are visualizing for static equilibrium problems, it's important to identify the object that you're trying to analyze. Often you're trying to find forces that are acting in a system. And there's an object that ties all the actors together. All of the forces in the problem. There's usually just sort of some central object. The one on which all the forces can be acting. So between you, your friend, the box, and the table, can you identify what the central actor is, the thing that is experiencing all the forces? It's the table. The table's got you, it's got your friend, it's got the box, right? So when we draw the force, now does the box have weight? Yeah. And does the box exert a force on the table? Yes. And does the table exert a force on the box? Yes. Newton's third law. That last one I just said, the table on the box. What do we call that force? The normal force. But we're not going to draw the normal force for the table. Right? The normal force acts on the box. The box acts on the table. And I'm just going to draw that. It's the anti-normal force. It's the Newton's third law interaction pair. But I draw it on the table. Now, it has the same magnitude as the weight of the box. It can't be anything else. There's no accelerations. There's no other objects pushing or pulling. But I draw it acting on that table itself. All right, so there are my forces. In order for me to be able to employ the sum of the forces statement, I do need to know which way is positive. So any choices as to what we're going to call positive x and positive y? Up is positive. It's so boring. I'm going to call this Boring Monday. All right? Now, remember, back when we were doing chapters 5 and 6 problems, I had a rule of thumb. How are you supposed to pick those positive directions? With the acceleration. There is no acceleration. So you're free to pick whatever you like. Doesn't matter. Except for the fact that there are easier choices than others, right? This one's pretty darned easy because all of our forces are only in the y direction, aren't they? If you have something that's tilted, you might want to tilt your axes, right? But again, the direction you call positive is going to be immaterial because there's no acceleration here. We don't have to worry about that one. All right, so then I come over here and I start doing the sum of the forces. Let's see. I start with MA, but MA is 0 in this case. I'll start with 0. I like doing it backwards, right? 0 equals. And then what have I got? Well, I've got force 1. Got force 2. I've got mg. Are you comfortable with that right there? Did I go too fast? This is old hat, isn't it? Find the forces, find their directions. Done. Okay. That's it. But what are we going to do about some of the torques? Okay. So in order to talk about a torque, what do we have to define? We need to define an axis, some point that we're saying, look, torque has to be defined as some force acting at some distance away from a point, an axis. So we've got to pick an axis, first thing. What's the other thing we need to define for talking about torque?
Radius.
Well, that's the distance from the axis.
What is how it's rotating?
Which way is positive? Just like we have a coordinate system for forces, okay? We need to be able to talk about which way is positive rotation. So as far as the axes are concerned, we pick one axis. And again, you're free to pick wherever you want. Are there two choices that are jumping right out at you as natural places to pick an axis? Where would you put an axis in this drawing?
The center.
Okay, there's the center.
The end.
The ends. Can you put an axis on Mars? Sure, don't do that. Either end or the center. Now, let me give you a rule of thumb for statics. Always put an axis where you have the greatest number of unknown forces. That rule later on is going to save our bacon. Right now, we don't know what F1 and F2 are. So we're free to choose either end, but we don't want to put it at the center. Because if we did, we'd end up with an equation with two unknowns in it. By putting an axis at the location of greatest number of unknowns, you remove them from the torque equation, which simplifies the math. You may not understand what I'm talking about right now, but you'll see this happen over and over again today. I'll be able to say, well, the torque of that force is 0, because we made sure the axis was where that force is acting. So, for purposes of picking something, I'm just going to go ahead and pick the left-hand side. Okay? I like to kind of put an X where I'm defining my axis, and sometimes, depending on how hard my brain is working, I might even label it and tell myself, okay, that right there, I mean, there's your axis, right? When you forget later, now you remember where it is. All right. So again, that's arbitrary. Is the table rotating at all? No, it isn't. But in order to define a torque, we do need to define it with respect to some point, some axis. All right. So, sum of torques equals 0. Oh, which way are we going to call positive rotation? Clockwise or counterclockwise? Clockwise? Feeling clockwise today? All right. Does that choice matter? No, but once made, stick to it, right? All right, so sum of torques. Start with 0. And then how many torques am I going to have with my axis on the left-hand side? 2. Why is it only 2? What is the torque that F1 is applying right now? Why is it 0? 0 distance from the axis, right? And again, that's where putting an axis at the location of the greatest number of unknowns saves our bacon, right? It eliminates that unknown thing from our statement. So, no torque from F1. What about mg? Does mg cause a torque? Sure. So I'm going to just kind of notate that. I've got I know it's causing a torque, and we'll go back later and define what that torque is. All right, what about F2? Can F2 cause a torque? Sure. So we'll go torque sub F2. All right. What's my next step in figuring out the torques? I've got to get the directions because I don't have an equation right now, right? I've left out the directions these things are acting. So how are we going to determine the directions of the torque? mg, positive or negative? How'd you do that? What your brain did, you may not realize it because it's too early in the morning, right? Is your brain said, look, here is the axis, right, on the end. And mg is either pulling down or pushing down. And if mg were the only thing acting, then which way would the table be rotating? Clockwise. So we're going to give that, oops, Don't ever write on your iPad upside down. We're going to give the mg a positive torque. Okay. What about F2? Negative? Why? If it's held down on one end and F2 is acting up, it's going to cause the whole thing to... Notice I'm eliminating all the others. I'm just ignoring everything else. I want to zero in on the torque of F2 in its direction, and it would cause a counterclockwise rotation. You also see that I'm holding up my pencil and doing that? What can you do on your homework? Exactly the same thing, right? Find the central actor, and if you got something like this, grab your, wherever your axis is, grab your pencil at that point, and then apply the force, and see which way it rotates, right? And that'll help you visualize the direction that these things are acting in. So stick a negative sign right there. All right, now that I know the directions, how do I write down these torques in a way that I can problem solve with? What is the definition of torque? It's either a cross product, which we really don't want to think about, or Mr. Balo's kind of way of thinking about things in that I need a distance that's perpendicular to a force, somehow, some way. So the distance to mg is right there, from axis to point where force is acting. And if we call the entire length of this table L, and that box is like 3/4 of the way along the table, right? It's closer to you than your friend. Okay, we'll call that 3/4 L. Then how am I going to write the torque due to mg? Distance is 3/4 L times the force. What's the force? mg. So that whole term right here is the torque due to mg. All right. Distance to F2. Total length of the table and the force? All right. So now we have two statements. We've got the black, which came from our linear way of doing things. And then we have the green, which came from rotational.
How did we choose like the F2 and the torque of F2? I was just somewhat confused with that again.
How did we write it down?
Or no, yeah, like why did we choose that? Like why isn't it like F1 in that case, the torque F1?
Well, because we put the axis at F1.
Oh, okay.
And that makes F1 be zero distance from the axis.
Okay.
And so if we take the length, 0, multiply by F1 is 0.
Okay.
So I didn't bother to write it in.
Okay. I just wanted to get that stuff.
Yep. All right, we want to solve for F1 and F2. How are we going to do it?
Plug in.
It's a math problem now. 2 equations, 2 unknowns. How are we going to solve it? Start solving. And do you notice something down here? What happened? It's just F2. If we had put the axis in the center, it would have changed the lengths, and then we would have had 2 torques, a torque from F1 and a torque from F2, and both of those would have been unknown. So we would have had to solve 2 equations with 2 unknowns. This time, because we picked smartly our axis at one of the unknowns and got rid of it, and I'm left with just one unknown in this statement, turns out that F2 is going to be 3/4 mg. What happened to the L? In every term, so I got rid of it. Doesn't matter how long it is. And that says F2 is equal to 3/4 the way to the box. And now how do I find F1? And put it in right there, right? So F1, and it's going to be 3/4 mg minus mg, which makes this F1 minus 1/4 mg, which means F1 is equal to 1/4 mg. There's F1, there's F2, problem solved, and what did we learn?
The axis.
Put the box where your friend's at. Have you ever moved a piece of furniture? Kind of looks like that. right? Which end's heavier? The one with all the files in it, right? Okay. That's the end, depending on what kind of person you are. Nice person or not so nice person, pick your end. Yeah, we found out what we already suspected to be true, right? The end that had the most weight on it is going to experience the most force. If we want to even all that out, we've got to slide the box over towards the center. This isn't like mind-blowing information, right? Wrong button. There we go. All right. So let's do something else. Okay. As always, a picture is worth 1,000 words, but oftentimes getting those words into pictures takes 1,000 hours. So what I would like you to do is try to draw the picture of this one. Just based on the writing right here, try to draw the picture. Try to see what the words are trying to tell you. And when you kind of think you got the picture down, share it with your neighbor. I'll give you a couple minutes.
Is the beam attached to the wall?
You decide. If you're stuck, if you just kind of like, I don't see it at all, I don't understand what's going on, turn to your neighbor, start talking about it, right? Ask for help. Is this what you got? Was this what was in your head or what was on your paper?
Yeah.
Okay, where did you run into difficulties?
There's oddly a wide, instead of being like sent, oh, I see how things
It's just worded ugly. Like for me, I would have thought that.
Okay, so Jade, hold that up so that, I don't know if everybody can see that. Okay. So I don't know if you can see it from where you are, but she drew her wire not attached to the end. It's like attached kind of towards the side, towards the middle, all that kind of stuff, right? Okay. So yeah, that's an excellent try, right? Okay. It doesn't say where the wire is attached, right? So that would be totally legitimate, right? But the idea is that it is attached. I mean, the place where the wire is going to have the most effectiveness, right, would be attached to the very end. Okay? So no, that's definitely fair, but we'll stick with this drawing right here. Other places where you got hung up, messed up, didn't see it. Where's the sign?
Yeah, that was like.
Yeah, is it like hanging by a string, or is it like hanging halfway along the beam or something like
I
that?
didn't like question that.
Yeah. So the reason I worded this one kind of vaguely was to kind of make a point here, right? A picture is worth 1,000 words. And when you're communicating with your fellow scientists and engineers, making sure that they understand it the same way you understand it, the way that you see it, you're seeing the same things, goes a long way to clearing up problems down the road. Right? So I guess what I'm trying to say is that you do need to pay attention to your writing classes. It's important. Okay, and whatever you do, don't ever vote for me. You do not want me for. Oh no, you do not want me for president because.
Exactly.
Well, the first thing I would do on my first day of office is I would make SUVs illegal. Second thing I would do is most fuel inefficient car in the world. The second thing I would do is make an executive order that said that sweatpants is appropriate professional attire for anybody anywhere.
I agree. Yeah.
Still down. All right. Oh, definitely. That's before I'd enter office, right? All right. So, in order to figure out, they're asking us for the tension in the wire and the force exerted on the wall by the beam. In other words, engineers would want to know, well, how thick of the wire should I use? Like, what's the tensile strength that the wire needs to support? And since I'm an engineer, if I find out what the value is, I'm going to then double it, right? Because I want it to be within the realms of safety. So knowing what these things are, right? Knowing the forces in the structure become critical. So the first thing we need to do is we need to ask ourselves, what is the central actor? What is the thing that's tying kind of all the forces together? When you get into statics in engineering class, you're going to actually have several actors that you have to chain together. But for us, at this level, we're just going to always have one. So what's the central actor? Turn to your neighbor and tell them what it is. All right. Somebody want to tell me what it is? It's the wall? Why is it not the wall? Because what? The sign is not pushing or pulling on the wall. It's also not the wire. Why is it not the wire? Because it excludes the sign and the place where the beam and the wall touch. Why is it not Mars? No, don't answer that. So what is it? It's not the sign. Why is it not the sign? Because the sign only exerts a force on the beam. It doesn't tell us anything about the wire or the wall. What's the thing that connects them all together? The beam. The beam is pushing on the wall. It's interacting with the tension in the wire. It's feeling the force of the sign. It's also feeling the Earth's pull on it, right? It's the thing that's experiencing all the forces we're trying to look for. We want to know tension. We want to know what's going on with the wall, right? So it's the thing that connects all of those together. Now, let's say you pick the sign or you pick the wall or something like that. When you draw the free body diagram, you're going to realize, oh my gosh, there's no sign force in it, right? Okay, like you'll be missing things. Okay, and that'll be a clue to you that maybe you need to draw the free body diagram of something else. So we're going to draw everything according to the beam. So name an object that is pushing or pulling on the beam. The sign. Where are we going to draw that force? On the far end. Which direction? down. So it's going to be mass of the sign times G, MSG. Okay, name another object that is pushing or pulling on the beam.
Earth.
The Earth. Does this beam have mass?
Yeah.
Yes, well, as a matter of fact, it says it's 20 kilograms. They don't tell me anything else about the beam, so I'm going to assume it's uniform, meaning its center of mass is where?
Middle.
In its center. So I'll go ahead and draw that right as close in the center as I can. M sub G, mass of the beam times G. All right? Name another object that is pushing or pulling on the beam. The wire. We're going to call that force. And which direction does it act? Up the wire. Along the wire. All right. Any other objects that are pushing or pulling on the beam?
Wall.
The wall itself. And what direction is that force?
I want to say in.
Well, yeah, okay, so the beam exerts a force into the wall, but we want to draw the forces that the beam experiences. So the force that the beam experiences would be like the normal force from the wall. Okay? All right. Couple questions. I insisted a long time ago, when we first started doing Newton's laws, when everybody wanted to go straight for forces, I kept asking you to do what instead?
Name object.
Name the object that causes the force. Why did I make you do that, Carlo?
So that way much just blurred out right.
Not blurt out random things. Because of today. You have to think about that central actor. And I've been having you practice that. Now, was it that big a deal back in chapter 5? No, not really. But that was a safe place to practice. Now, when you're trying to draw your diagrams for static, you've got to think about all the objects that are pushing and pulling on that central actor. And then be able to figure out what that force is. Is it a normal force? Is it a tension? Is it the force of gravity? Right? Whatever it is. And draw the directions correctly. How many of you wanted to draw the tension straight up? Yeah, right? Instead of along the wire. Tension only acts along the rope, right? Or along the wire in the direction of pull. But this diagram now needs to be checked for several things. It's not complete. We haven't picked positive or negative or axis or anything. But you want to stop at points along the process and ask yourself, have I drawn something where it is possible for this object to be in equilibrium? There's two things you got to check. Is it in translational equilibrium? Are the forces balanced left and right and up and down? And then the second question is it in rotational equilibrium? Is this thing going to rotate? So, let's tackle the translation equilibrium first. Do I have any forces that are not counterbalanced? In other words, if I've got a force pointing down, is there at least one force that points up?
Yes.
Which is the one that points up?
Tension.
Tension. Tension has a component that points up? Okay. Maybe we should go in and just draw those components in right now. Because I think you know what our axis is going to be. Let's go ahead and just define it right now. We'll use a standard, oops, that's not Y. X and Y axis. The beam is perfectly horizontal. If the beam were tilted a little bit, I'd probably want to tilt my axes, but it's not, so we'll deal with it right there. So I've drawn out the components of T right there. We'll go ahead and label them TY and TX. All right, so there I can see that I have an upwards force and downwards forces that could cancel each other out. All right, we got to check the same thing for horizontal. For it, do I have at least, if I've got a force pointing to the right, I need at least one force that's pointing to the left. And do I have that? Yes, so it's not a guarantee, but at least if we didn't have TX, right, and all we had was that wall force that's pointing off to the side, I'd be really worried at that point. I've got a force pointing in the positive x and nothing to counterbalance it. It's impossible for it to be in equilibrium if I don't have forces adding up to 0 in both the x and y directions. All right, what about torques? Are there, for any axis we define, and are there two places that you're kind of going, I want to put an axis somewhere? The wall or at the end?
Wall.
Either end, right? Okay? Because there's going to be unknowns there, right? We've got this wall force, we've got the tension that we don't know, right? And that's kind of what we're looking for, right? Tension and wall. So we want to put that right. So look at both ends and ask yourself, okay, do I have torques that can balance each other? Right? So if I put the axis on the left-hand side, right? Do I have torques going clockwise? Yeah, and do I have at least one going counterclockwise? Yeah, so there's the possibility of balance there. If I didn't have Ty, again, I'd be panicking. I'd have to go look for something else. All right, if we put the axis on the other end, okay, do I have torques that are balanced? No?
Ty would be 0.
Okay, if I put the axis where Ty is, and MSG and Tx, right, the torques of all three of those go to what? Go to 0. What about the torque from MBG? Would that be clockwise or counterclockwise? Hold your pencil up, right? Okay, you've got the beam. We're holding the beam down at this end, and MBG is pulling down. So it's a counterclockwise torque. Where's the clockwise one to counter it?
Do you mind saying that one more time?
Sure. I've got a beam. And I've got an axis that I'm pretending I'm putting at the right-hand side. The only force causing a torque is MBG. And it's causing a counterclockwise rotation of the beam. And it's the only one. What does that mean? It means it cannot be in equilibrium. We've made a mistake. We're missing something. Let's go back. I'll get to your question in a second. If we put the axis on the left-hand side, right, I'm holding my pencil, do I have the possibility for balanced torques? Yeah, right? MBG would be clockwise, MSG would be clockwise, and TY would be counterclockwise, right? I've got both clockwise and counterclockwise torques, so I'm good. But it's when I went over here for my axis, I realized, I've only got one torque with the axis on that end. And I need to have the torques balanced everywhere for all choices of axes. Jade, and then somebody, and then Hunter. Okay. There's another one out here. No, Hunter.
Oh, I was going to suggest where I think we're missing a force.
Yeah, where do you think the force is?
The wire and the wall.
Oh, up here?
Yeah.
Nope. There is a force there. I'll give you that. It's tension. Okay? But that's not connected to the beam, right? That's the wall and the wire. That doesn't help us. Yes. Between the wall and the beam, in what direction? Upwards? And how'd you know that, Elidie? We need it to balance, right? Like, let's think about how we would connect a bar to a wall, right? Okay, we've got a string holding onto the top there. And what do I need at this end to hold this end of the stick up?
Friction.
I either need friction, and if there's no friction, what is it going to do? It's just going to fall down, right? So there needs to be like a pin or a support or a block or something right here. But that pin, that friction, that block, whatever it is going to be applying a directly upwards force. I've got the normal force from the wall, right, coming in this way, but I need to have a vertical force to hold this thing. Otherwise, whoop, it's just going to fall out. So I'm going to call those wall X and wall Y. Now you may be sitting there saying to yourself, how was I supposed to know that? What process did we go through in order to figure out that we were missing something? we put axes in lots of different places, didn't we? Okay? Don't be satisfied with just one. Okay? Pick a couple, pick 3, and go through the process. It's a conceptual process, right? Of trying to make sure that I've got balanced forces and balanced torques. Remember, that's the rule in equilibrium. In your statics class, you'll be learning different methods for going through and being able to do that, to make those choices. And make sure that you haven't skimped on any forces where you've got things coming together, and so on and so forth. My goal is by the time you get in Dr. Adams' class, statics is easy. Just like, oh yeah. All right. We need to pick an axis. Where should we pick the axis for our analysis? The wall or the tension? Where do you want to put the axis? What did I say? The point of most unknowns. We don't know Wx, we don't know Wy, we don't know Tx, and we don't know Ty. So I've got 2 points. I've got the left and right ends of the beam. Both points have 2 unknowns at them, so it really doesn't matter which end I pick. I'm going to go ahead and pick the wall. I feel like it's almost a natural place where there might be a kind of rotation, right? There's probably a pin or something there that's holding it up. And when the wire breaks or gets cut or overloaded or something like that, the whole thing will rotate down.
Why are we not including the x component of the tension?
We are.
Oh, so what?
I haven't written it down yet, right? But
In doing our T component, does it really matter if we put our Ty inside the triangle?
right, you can draw it at the end or you can draw it over here on the side. The point, though, is that where does it act? Ty, where is it acting? At the very end, right? So if I drew it at the triangle, I might forget that Ty is acting at the very end of the beam, which is why I try to draw it where it acts. All right. There's my axis. Which way do you want to have the positive rotation?
Down.
That's not a direction for rotation.
Oh, counter.
Clockwise or counterclockwise? Counterclockwise this time? We did clockwise before. We got to keep things even in the universe and balance. So always recycle your electrons. All right. So we'll go ahead and pick counterclockwise this time for our positive. And away we go. What are we going to write down now? What's our strategy for figuring all this out? We are going to write down some of the forces are being 0. And then we're going to write down some of the torques being 0. In the case of forces, this time I do have 2 directions. I've got X and Y forces this time. Last problem only had 1 direction. So in the X direction, so easy, 0 equals. And now you just write out your forces. How many X direction forces? 2 of them. Did I get the directions correct? Yes. All right. In the Y direction, what have I got? I've got WY, MBG, MSG, and TY. Check my directions. Did I do okay? I got the downy ones with negative signs. I got the uppy ones with positive signs. Okay? Then, the part that I kind of consider to be the newer part for you, right? You've had lots of practice and lots of chances of writing down forces, but not so much with torques. Okay? Torque is kind of a different animal now. So, let's go ahead and break this one down into its pieces parts. Okay? My axis is over here on the left-hand side. How many torques are there with respect to that axis? There can be a torque from MBG, a torque from MSG, a torque from TX, and a torque from TY. Why am I writing all those down? Because they're not 0 distance from the axis, right? Why didn't I write WX and WY? They're at 0 distance from the axis. Okay, now, some of you got a look on your face like one of these is wrong, Mr. Balo. We'll get there. I'm being complete. You don't have to write down the one that's 0, okay? But there is one here that is 0. Let's talk about the directions, though. MBG, use the pencil trick. Determine the direction of torque for MBG. So you're grabbing your pencil, holding it on the left end, and either pushing or pulling down. So which way is that making the beam go? In the negative direction. We define positive as counterclockwise, so we're going to put a negative sign on that torque. All right, what about the sign? Sign. Same sign. Too many S sounds. Okay. All right, what about TX? No rotation for TX? TX is parallel to the distance from the axis. In order for there to be torque, what do you need? Perpendicular. So what do we write down for TX? 0. And then what about TY? Do the analysis with your pencil. Don't just go, well, I got 2 negative ones, so the next one has to be positive. Make sure that that's what your diagram is telling you. Okay? All right. Now I've got to go through and define mathematically what these torques are. They're distance times force. What is the distance to MBG? Half the length, whatever it is, of the beam. They didn't give me the length of the beam, did they? Interesting. And then I put the force in. M sub B times G with a minus sign. Minus. All right, what's the distance to the sign? L. And it's MSG. All right, and what's the distance to TY? L. And the force? TY. And there we go. I have 3 equations now, don't I? How many unknowns are there? Well, WX and TX, WY and TY. This one down here already has a TY in it, so I'm not going to put a check mark on it. I've got 4 unknowns. How many equations do I have? I have 3. Is this doable? No. We need another equation. Where are we going to get it? Don't say fun. No. It's not fun. Is there a clue in something we haven't used yet? Theta. Don't think about it. For TX, do you use sine or cosine?
Or X.
Cosine, why? It's touching the angle! For TY?
Sine.
Why is it sine? Because we already used cosine, because it's not touching the angle!
Hey, Mr. Balo. What's your number?
That always works. I've never seen a case where that doesn't work. And that's how I just do it without triangles now, right? I don't have to draw the triangle. I can draw where it acts and then just look and see if it's touching, not touching. Done. All right. Now do I have enough? Yes.
I don't like being screamed at.
It's your choice. I enjoy the screaming. All right. As long as it's me and not you. Right? If you're screaming, there's a problem. What has to happen at this point is algebra. Okay? But I don't want to do all that algebra because number one, I'm a lazy person. Number two, I've got other things to show you. So, when you do a bunch of algebra, what you get is the wall force is 707 newtons at 8 degrees. 8 degrees. And then the tension is 855 newtons, and we already know the angle for that one. Why does the wall force have an angle? we found the components of x and y at the wall, didn't we? So when you find wx and you find wy, how do you find the magnitude? Pythagorean theorem. And how do you find the angle? Inverse tangent. We've all done all that before. Okay?
So the wall's not straight?
Nope. It's got components. It's got x and y components that aren't 0. You find wx, you square it. You find wy, you square it, and you square root it, and then you take the inverse tangent
Okay.
to find the angle. That's standard vectorness. Vectorness. The word. All right, I predict. Well, we'll see. This example might bleed over into Wednesday, but Wednesday I will finish up. If I don't finish it today, I will finish up chapter 12 on Wednesday and start chapter 13. When is your next exam?
And that, no, 2 weeks.
2 weeks from.
This Thursday.
I can never remember what today is. It's still October. We have a holiday. 2 of them coming up in November. One of them is Veterans Day. Veterans Day is on Sunday, but it's observed on Monday. Because if you deny Americans a holiday, then we're even worse than Europe. So we're not meeting that Monday. What is that, 12?
Yes.
So we're not meeting that day, and that Wednesday is your review for the test you're taking on Thursday of that week. Okay? So we're minus 1 day, which is why it's going to be speaking. So basically your test is 2 weeks from last Thursday? 3 weeks from last Thursday. This lab.
Gosh.
So we have 2 labs and then the test. Believe me, I looked at the calendar this morning. I just can't remember it anymore. Yeah, we have lab 2 this Thursday, and then we have a lab on the 8th, and then your exam. So your exam's on the 15th, right? So that was 3 weeks from last Thursday. Horrible. All right. Let's talk ladders. Okay? So, when a ladder is, don't ever do this with a ladder, unless it's designed to do it. Okay? This ladder is not designed to do this, but I didn't have any other kinds of ladders. Okay, I'm going to really exaggerate what's going on here. Okay? Yeah. Protect the interpreter at all costs. So, talk to me about the forces that are acting on the ladder right now.
Friction.
There's friction. Because if there wasn't friction, what would happen? Right? Okay? So we know there's friction between the floor and the ladder. Okay? What else is down here? A normal force, right? Pushing up vertically from the floor, because the ladder and the floor are in contact with each other, aren't they?
Yes.
Okay? What else? The wall. So is there a contact between the wall and the ladder? Which way? Perpendicular, so it would be straight out from the wall. Is there another one?
Yes.
Yeah, there's one, because it's kind of resting on the lip of the door frame. So there's a force pointing up like that. Okay? So lots of forces going on in there. And then you put a person on top of that. Alright. Let me simulate a wall. This is a simulated wall. Right? So as a person climbs a ladder, right? What happens to the forces on it? Are the forces any different based on which rung I'm on?
No.
No. Is the normal force down at the base of the ladder going to change just because I've got higher on the ladder? No. Am I exerting a force on the ladder? Yes, right? Downwards on the ladder, ladder upwards on me. Okay? What's changing as I go higher and higher?
Torque.
Say it again, Carlo.
Torque.
Torque. Why is the torque changing? I'm getting further from or closer to some axis point, right? Okay? And so torque changes depending on where a person is on a ladder, but the forces don't. If you can kind of wrap your brain around that, you'll be a little bit closer to mastery and understanding. But let's draw a picture of this painter on her ladder. Let's see. So, got a wall, got the ground, and then I have the ladder. Now, they do tell us something special about the wall. Why are we doing a frictionless wall? So we can be careful. So we can make it as easy as possible. Okay? Because this one's hard. So that means that at the wall, we have only one force. And what direction does that force act? Let's save that one for later. Let's save that one for later. Can we do the force at the bottom of the ladder? Okay, so which direction is the normal force? It's up. Oh, and why are we drawing the free body diagram of the ladder? It's the thing that connects everything, right? Forces at the ground, forces at the wall, force of the painter, everything. It's all connected to the ladder. All right. We got a normal force. What direction is the friction acting?
This way. That way.
Because it's trying to go this way, so I guess it's too long.
What does the base of the ladder want to do? What direction does it want to go? It wants to slide out.
So it's going to be pushing forward.
So what direction does the force of friction act on the ladder? Towards the wall or away from it? Commit.
Towards the wall.
Towards the wall?
Yes.
You're all right. Okay, it is towards the wall. The ladder is pushing on the ground away from the wall. And according to the song, if the ladder exerts a force upon the ground away from the wall, this is version 2 is a cover. Okay? Then the ground exerts a force on the ladder towards the wall. Okay. That's not easy, is it? How much concept is going into these problems? The answer is all of it. Like, the only thing we haven't talked about is energy, right? Okay. Momentum. So, all right. Painter. Where's the painter? 3/4 of the way up the ladder, right? So, what direction does the painter exert a force on the ladder? Down. Call that P for painter. I could have done mass of the painter times G, but see how they've given me the actual force, 650 newtons? I'm not going to break that down into mass and G, right? I just know that P is equal to 650 newtons, right? All right, what about the ladder itself?
Ladder.
It's the weight of the ladder. Where is it acting? Direction is down, and it's in the center because it's a uniform ladder. Okay, and now we get to the wall. We know there needs to be a force there, right? Okay, so the question is, what is the direction of that force?
Right.
Looking at the diagram, can you see an unbalanced force? X or Y direction? It's X. I only have a force pointing to the left. What do I have to have? A force pointing to the right. Where am I going to get it? The wall. I'm not going to invent it. I'm going to think about it. The wall and the ladder come into contact. When two surfaces come into contact, what force do we call that? A normal force. And normal forces always point perpendicular to the surface of contact. All right. Why is there no vertical part to that force? It says it's a frictionless wall. If it's frictionless, there can be no force of friction. Forces of friction act in the plane of contact. There's no friction here, so we're not going to worry about it. If there was friction, then what direction would the friction be acting? Up or down? Up. The ladder's trying to go slide down, right? The ladder wants to slide away, like down and away. So the friction's going to be pushing up on the ladder to keep it from sliding down. All right. Here's our forces. What do we need in order to do our analysis? We need axes and what else? Direction for torque. So why am I having trouble? I got this ladder that's got like an angle to it, right? Right? They've given me that angle, I think, right? Theta right down there. But I've got a lot of forces that are already kind of straight up and down, right? All my forces are already in X or Y. So I think I'm just going to stick. Keep doing that. Dyslexia is strong this morning. So I think I'm going to stick with that one. That would keep me from having to find components, right? Of these forces. And then what about an axis? Where do I want to put the axis? Kind of do bottom or top, like where, what's unknown here? We don't know W. We don't know N. We don't know F, right?
But we want to find.
Oh, but we want to find F so that we can find the coefficient of friction, because we know coefficient is fun, it's hiding inside fun. So we don't want to eliminate that. Or do we? The rule of thumb was what? Most unknowns. Even if the thing we're trying to find is down there? Yes. Okay? Do that. Even if it seems like it's taking out the thing you want to find, you really want to put it at the greatest number of unknowns. Because there's that math that makes the problem mathematically simpler to solve. You'll be able to get back to what you want to get later. Now, if you're only writing down the torque equation, don't do that, right? If you only got one equation, then the thing you're solving for has to be in it. But when we're going to have the case of multiple equations, then always put it at the greatest number of unknowns. And hope that it works, because if it doesn't, you got to redefine the axis and do it all over again. All right, so some of the forces. We've got the x direction. W minus F, did I do that right? Yes, no? Yeah. So only two horizontal forces, and W is positive and F is negative. So I'm good with that one. In the y direction, let's see, what have I got? I've got, looks like I've got N, and I've got P, and I've got L. And the P and L are both pointing down. So I'm going to give them negative signs. And normal force is pointing up, so I'll give a positive sign. Okay.
Excuse me.
Yeah.
Since we make the bottom of the ladder the axis of rotation, then why do at that point the forces acting they are zero? Then why-
Torques are zero,
Sorry.
but not forces.
Oh,
Yeah, right? We're doing, yeah, this is good. This is very good. I'm glad a lady brought this up. The zero trick for the axis only works for the torque equation. Don't do it for the force equation. Everything's zero. My life is good. Okay? Your building's falling down. We don't want that. Okay.
You haven't defined a torque yet.
I haven't defined an axis, have I? A direction. I've got the axis down there, right, at the bottom. But I need a direction. So clockwise or counterclockwise?
Clockwise.
Clockwise? Kind of bouncing back and forth in our directions. Yeah. It's fun.
Clockwise is
Okay, okay, fine. Clockwise. Does it matter? No. Because we don't have an acceleration, so I don't have to worry about checking that direction. So pick something. Stick with it. All right. What is that torque equation going to look like now? First of all, there are F and N in it. Yep. So the torque due to L, there's a torque due to P, and there's a torque due to W. Agree or disagree?
Agree.
Okay with that? Those are the three things that can have torque, right? Torque due to L, positive or negative?
Positive.
So I've got my, get your pencil out, right?
Negative.
Hold it down here at the bottom. What direction is L? Down. What kind of rotation does it cause? A counterclockwise rotation. We said clockwise was positive, so negative sign. All right, what about P?
Same.
Also counterclockwise, so negative. So I'm just going to write positive on that one because it has to be. No?
It's 0.
What am I going to do? I'm going to check. My axis is down at the bottom. My W force, pushing at the top. Clockwise rotation, positive.
So why was it 0 last time?
I was what 0 last time? The wall force?
Yeah.
Because we put the axis at the wall. Wherever you put the axis, that's what's 0, right? Everything else is going to have a torque of some kind, unless it's completely parallel to the distance. All right. The next thing we have to do is write down what?
Friction.
We have to actually write down what these torques are. It's not enough to just leave them as tau. We really can't do anything with them as taus. We need to have distance and we need to have force. But what do those things need to be? The distance and the forces have to be what? Perpendicular to each other.
So we need
The distances.
We had to find magnitudes.
Okay, so there's two ways to think about this. And I'm actually going to do both ways. I'm going to run out of time to do both ways, so we're going to pick it up again on Wednesday. I'll do the second way. But there's two ways to conceptualize these torques. We can find the component of the force that is perpendicular to the distance, or we can find the perpendicular distance to the force. They turn out to be exactly equivalent to each other. It's simply a question of how you want to picture and conceptualize these torques. What I'm going to do right now is we're going to find the perpendicular components of the forces to the distances, because that's the one you have the most experience with. On Wednesday, I'll come back and do it the other way. Let me get a blank thing. I know everything disappeared, but I want to make this drawing as big as possible so you can see what's going on here. So I've got my axis down here. Let's do L first. There's L, right? So the distance from the axis to L goes up along the ladder right there, and it's the length of the ladder divided by 2. Half the length of the ladder. Okay. Do you see how that distance and that force are not perpendicular to each other? So what we're going to do is we are going to find the component of L that is perpendicular to that distance. I drew a perpendicular line, and then I've got to find the component of L that acts along that line. You've done this before. If the angle down here is theta, then what is the angle right there? It is also theta. That's just like our hill problem, right? And so what is this component going to be? Sine or cosine? Cosine, because it's touching. Okay, then we do the same thing with P, right? The distance to P. 3/4 L, right? And then what component, sine or cosine of P, are we going to use? It's going to be cosine. P cosine theta. All right. What about W? Kind of making this messy. Here's the top of the wall. Okay. There's W. We have the length coming up from the bottom, which is going to be L. We need which part of W? That one. The angle at the base of the ladder is there. So where do I draw the angle theta? Up near W.
From the length of the W.
Right there?
Yeah.
That's called alternate interior angles are equal. You have two parallel lines and another line connecting them. The alternate interiors are equal to each other. So, for the W force, which component, sine or cosine? Why sine? It's not touching that angle. The perpendicular component of W is not touching that angle. W sine theta. So from those drawings, now that I know that the component that is perpendicular to the length is L cosine, P cosine, and W sine, I can come over here and I can write out what these torques are. The torque due to L, distance, L over 2, times force, L cosine theta. Then, distance to P, 3/4 L. And the component I need, P cosine theta. And finally, distance to W, L. And then the sine, W sine theta. Needing to find the perpendicular components. And this is why, so I'm hoping that the L cosine and the P cosine felt natural to you. We've done that a lot, right? With all the hill stuff, right? And the geometry problem you did in lab number 1 and all this, have kind of been reinforcing that concept the whole time. So those are right. The W sine one might have thrown you a little bit, right? It's a new geometry, so to speak. Right? But hopefully you can see, even if you don't believe me about the alternate interior angles, which you should, that's a math thing. Don't take my word for it, go ask your math teachers. Maybe don't go ask your math teachers, just take my word for it so you can avoid that conversation. But you can see that it's not touching that angle, and I need that component that's perpendicular to the distance that's along the ladder. So maybe you can believe W sine theta. Those considerations are really important, but this is something that points out the flaw in trusting RF sine theta. Do you remember that definition of torque I told you to be careful about? You don't want to use RF sine theta because the theta in RF sine theta is not the theta in this picture. Okay? And so that's where the problem crops up. I'd much rather you fall back on a skill you already know. You know how to find these components perpendicular to these lengths. Okay? So that's a realm of safety. Now on Wednesday, I'm going to pick up right here and I'm going to do another method. One that's actually favored by most engineers I've noticed. Okay? And that one will melt your brain a little bit. And then when I'm done with that, we'll move on to chapter 13. A great rest of the